Well, good evening all, and welcome to Roger, G3MEH. Thanks very much for coming this evening. So, without further ado, I will pass to Roger.
Right, good evening all. I think a lot of you probably look on me as a VHF-UHF operator, which is largely true nowadays, but I started my amateur radio career on the 160 metre band, top band, many years ago. I had a fair amount of experience on that, and got enough QSLs together to qualify for WABC, worked all British counties. I think there were about 90 in those days before the government got its hands on them. And I provided proof to Shortwave Mag, I don't know whether they're still going, of proof of contacts with 60 of them. So I have been around on the lower frequencies, and even nowadays I have been known to come up on 80 metres and more recently 40 metres to support the club in the January HF AFS contests. So that's a little bit about me. So before I talk about aerials, what are we trying to achieve? Let's briefly look at propagation, if I may. HF propagation is what happens is very frequency dependent, and I'm going to take some shortcuts, if I may, as far as the ionosphere is concerned, and ignore the fact that there's normally more than one layer, and just consider it as one. So I hope that's going to be acceptable. Anybody who's not familiar with that, you can easily read up the details if you wish. Right, so starting at medium frequencies, top band, if you've got a nice vertical aerial, you will be propagating a ground wave. That will get you significant distances, 50, maybe 75 kilometres on top band, it follows the ground literally as a result of diffraction. It'll find its way around objects, and it'll find its way to follow the ground. How effectively it follows the ground depends very much on the ground conductivity. In this part of the world, not too bad. If you go down to the West Country where you've got loads of granite, don't expect to get quite so far on ground wave. Ground wave is peculiar to the lower frequencies. The distance you can travel, the wave travels by ground wave, decreases very rapidly with increase in frequency. So probably top band is the only one for amateur, and if you're on the VLF bands, of course, those. But on the normal HF bands, probably top band is the only one where that's really relevant. For propagation on the higher frequency bands, and indeed on top band after dark, we're talking about signals being bounced back by the ionosphere. Now the ionosphere is what happens in the ionosphere is very frequency dependent. At low frequencies, it absorbs signals very well. As you go up in frequency, it starts to turn signals back until you eventually reach a frequency where, like the proverbial cliff, it all stops. You drop off the edge. What that frequency is, obviously, well, sure you're aware, depends on the sunspot cycle, depends on time of day, the time of the year, and but for us here, in connection with aerials, what's important is that it varies with the angle at which you propagate signals. If you propagate vertically upwards, then you have a specific maximum frequency, which is known as the critical frequency. And of course, anything that goes straight up, what goes up must come down. So that's very good for working locally, and critical frequency is very relevant to that. But that has impacts on the aerial you choose to do that with. As you go away from a vertical aerial, as you come down towards the horizontal, then the maximum frequency at which signals are turned back by the ionosphere increases until you get to the horizon. If you propagate horizontally, then that's the maximum frequency. Obviously the ground gets in the way, you can't do any better than that. And that is referred to as the maximum usable frequency, MUF. And in between, I've never seen the physics, any discussion of the physics involved with that, but in my experience, the MUF is 2.5, 3 times what the critical frequency is. So it's a huge difference between the maximum frequency at any one time that the ionosphere will turn back from vertically to what it will turn back horizontally. If you propagate horizontally, then you hit the ionosphere, and it will then bounce back at the same angle that you hit it, which doesn't take you all the way around to the other side of the world. If you want to do that, then you have to rely on multiple hops, as they are referred, and how effective they are obviously depends on not only the ionosphere, but also what's happening on the ground. If you hit the ground, then that's nothing like as effective. You'll lose a lot more signal than you will over seawater being pretty conductive. Coming to the aerials which we need in order to take advantage of this propagation on HF, vertical or horizontal. Horizontal aerials are affected by the ground. My VHF, UHF book says that to those frequencies, well, any frequencies, not to be too affected by the ground. The problem is that you launch a signal horizontally with an aerial, and that hits the ground, some of it, and bounces back up again, and you get interference between the two. So that is a problem, and that the combination of the two tilts the main beam upwards. So horizontal aerials are wonderful for vertical incidents or near vertical incidents where you want to propagate up and down again for local and semi-local QSOs. And indeed, the ground acts as a reflector, so that encourages signals upwards with a horizontal aerial. Some people on HF use beams, and you might possibly expect a beam to work at HF in a similar way to you've experienced at VHF and UHF. If you do, you're going to be a bit disappointed. As I was about to say and lost track a minute or so ago, you need, in order not to be too affected by the ground, the recommendation is that a beam should be at least 3 wavelengths and ideally 5 wavelengths. That's on 2 meters, between 6 meters and 10 meters above the ground. On the 10 meter band, what's that, 3 times 10 meters, 30 meters, about 100 feet as a minimum, and ideally, ideally 50 metres, 160 feet. Vertical aerials are obviously least affected by the ground and less tilted, get least upwards tilt. They have minimum propagation off the top. So if you're looking to work locals by near vertical incidents, straight up or nearly straight up, then don't bother. And as going back to the friend I used to know, no longer with us, he used to delight in, as conditions were changing on HF, as the maximum usable frequency was decreasing as a result of changes in the ionosphere, what he found was that when people with beams whose main lobe was pointed upwards significantly, when the frequency at which they could work dx had come down to the borderline and just beyond, because they were tilting slightly upwards, he had a vertical, and that enabled him for a quarter of an hour or so until the MUF came right down to the band he was on, enabled him to work stations that the big boys couldn't, because they'd lost it because of the upward tilt of their beams. So there we go. So basic types, very basic. I'm only going to talk mainly about simple aerials, by the way. I know nothing about the likes of boxons and cobwebs and things like that, clever things like that, but I think you have a club member who's fairly familiar with that area, so if you want to talk on that, then I suggest you buttonhole him. Right, so basic types of aerial, the vertical aerial, a bit impractical on top band, the shortest vertical aerial, the quarter wavelength, which is about 40 metres. Yes, a quarter of 160. Not many people are in a position to. Not many people are in a position to do that, but certainly on the higher frequency bands, a resonant aerial, vertical aerial, is very practical, and as I've just said, can be very useful for working the DX. Probably the most two common used aerials. There's a horizontal centre-fed aerial, and that's normally half-wave long. Half-wave length is the shortest length, which by itself, without any other help, is resonant. Quarter wave, you have to do something to anchor it down, as it were, and take the place of the other missing half. But that's another matter. It can be horizontal, it can be sloping, inverted V, or you can bend the ends round to fit in the garden if you can't fit it all in. They all work reasonably well. Another commonly used aerial is the inverted L, where you feed a bit of wire at the bottom, take it upwards, and then what you can't accommodate because of height limitations, you take along horizontally. All right. Now matching. Let me mention that briefly. Most transceivers, linears, etc., are designed to have a load of 50 ohms attached to them. You can remote the load by using a piece of 50 ohm coaxial cable. That's absolutely fine. the 50 ohm coax is, apart from slight losses at HF, is pretty transparent. So the rig will see a 50 ohm load on the end of it. It's difficult to achieve that exactly with some kind of aerials, or forgive me for talking about aerials rather than antennas, I'm afraid, but I was brought up on aerials, and I'm not American, so I carry on using that, so please forgive me. But the problem then is that the RF that's going down the coaxial cable from your transmitter, it would like to see a 50 ohm load on the end. If it sees something different, then not all of the power from your transmitter goes into the load, whether it be a dummy load, an aerial, or whatever. Some of it is reflected back along the coaxial cable. The outgoing and incoming power interact, so you get maxima and minima as you go along, referred to as standing waves, and the power that gets back to the transmitter wasn't expecting to have to deal with, and that can be a problem. It can cause overheating, can damage the rig. Now, most modern rigs, in my days, that was a significant. When I was involved with these things, considerably, rigs were fairly straightforward, and if you got it wrong, you blew the output stage of the rig up. Nowadays, most black boxes and linears have SWR, standing wave ratio monitoring, and if they don't like what they see, they will partly shut down the power. They will automatically reduce the transmitter power or the linear power to what is safe for the rig you're using. So that's less of a problem, but of course it is a disadvantage. Two ways of achieving a good match. One is to design the aerial to be a match to 50 ohms in the first place. The other is to accept whatever impedance the aerial presents and use a device known as an aerial tuning unit or an aerial matching unit, which converts the unacceptable impedance of the aerial into 50 ohms, so that you fool the transmitter into thinking that that by what you interpose in between, you fool it into thinking that there's a 50 ohm load on the end. Right. So the shortest length that will stand by itself is a half wavelength, and you'll see behind me, hopefully, if my head's not in the way, something that you may not be aware of, that the wavelength to diameter ratio affects the properties of the half wave dipole, half wave end fed. A long thin one is about 70 ohms. As you come down, it reduces to 60 ohms. That's perhaps not so important. What is perhaps more important is that the length of resonance varies with how thin or how fat the aerial is. You see the figures there. It's getting close to the theoretical half wavelength for a nice thin wire. For a much fatter one, as you might encounter at VHF, it's significantly shorter. The best advice I can give is if you're home building dipoles is to start with the maximum length and then trim it down, measure the SWR, and then trim it down in stages until you get optimum SWR on the frequency that you're aiming for, which in most cases I guess would be the middle of the band. Right. Rig AMUs are built into many rigs nowadays, have been for some years, typically only match up to an SWR of 3 to 1. So an antenna aerial that you tried to produce being a reasonable match, but you perhaps fell down a bit on, that shouldn't be too much of a problem. If you engage the rig's internal matching unit, it should cope. Right, another interesting thing is skin effect. Now, most people are quite happy that at DC and 50 hertz, the larger the cross-section of the conductor, the lower the losses. So if you want to carry more current without it heating up, you put a larger diameter conductor in. And indeed, mains cabling is specified by a conductor size, 2.5 mil, 4 mil, whatever. However, at RF, as you go up in frequency, from audio frequencies upwards, increasingly the signal doesn't like the middle of the cable, it clings to the outer layer. And this is known as skin effect. That is why at VHF tubes are used commonly for beams. You don't lose anything from the middle being missing because the RF doesn't use it, and of course it cuts down on the weight and the cost. I've got here, if I can pass this round, a piece of coaxial cable where the manufacturer has taken advantage of skin effect. Piece of 15mm diameter coaxial cable, which I use on 23 centimetres and 13 centimetres. If I can pass this around, if you look at it closely, you'll find that it's copper-plated aluminium. So what the RF sees is the copper, but to bulk it out, rather than having to use a tube, which obviously will fold up if you're not careful, aluminium has been used, which is obviously considerably lighter as well. So if you feed your half wave in the middle, you've got an impedance which varies between about 60 and 70 ohms, which is an adequate match for rigs to be fed with 50 ohm cable, though you have got a balance to unbalance problem. I'll come to that in a bit later on, if I may. The amateur bands are harmonically related, so if you, for instance, put up an 80-metre dipole, then at 40 metres it's 2 times half wavelengths rather than 2 times quarter wavelength. It's a full wavelength fed in the middle, so it's high impedance in the middle, which is definitely not what you want. The exception to that is the 15-metre band, which is 21 megs, and 21 is 3 times 7. So if you put up a 40-metre dipole, a half-wave dipole, then at 15 metres it's 2 times 3/4 wavelengths long. So although it's got a different polar diagram, it will give you a very reasonable match. Most of us, of course, want to operate on multiple bands on HF, and obviously a single straightforward dipole, unless you put up a 40-metre band half-wave dipole, which will also cover you for 15 metres, it's going to leave you up the proverbial creek on other bands, because they're going to be very high feed point impedance. So what sort of multiband aerials are available? Well, the first thing you can do is to put up several different half-wave dipoles, connect them to the same feed point, and spread them out a bit, and extend the length of the shorter ones to a spreader of some sort. It's referred to as a nest of dipoles for fairly obvious reasons. I've only drawn 3, but you can put more than that up, and obviously with any one dipole only being a low impedance at the frequency at which it is half wavelength long overall. That's in relation because of the harmonic relationship of the amateur bands, apart from, of course, 40 metres and 15 metres. Then the unused dipoles have negligible effect. So that's one way of doing it. Another common way of doing it is what's known as a trapped dipole. What you do is you make yourself a half-wave dipole for the highest frequency band that you want, the shortest dipole, and you then put a parallel tuned circuit at each end of it, which at the frequency of the half-wave dipole presents a high impedance, so isolates it from whatever else you may add to it. You then add some more wire to it for the next frequency down, and do the same thing again, and you can cover all 5 HF, the main HF bands without any problem that way. It's only a single conductor, broken up, of course, for the traps. The disadvantages are the weight of the traps, and also the power rating of the traps. It's a parallel tuned circuit, so there will be some quite high voltages present there. And the other problem is, from a practical point of view, is the difficulty of waterproofing it. I've heard of people who have put up lovely trapped dipoles only to find that after some torrential rain that it didn't work quite as well as they were expecting it to. An advantage of it, however, is that taking the highest frequency band, going to the next band up, the parallel tuned circuit is no longer resonant, and it acts to some extent as a loading coil, so you don't need to add as much wire as you thought you would to achieve resonance on the next frequency band down, and so on. So the overall length of a trapped dipole is significantly less than a half-wave dipole for the lowest frequency band would be. Then there are other compromise aerials. There's the well-known Louis Varney's G5RV, which is a bit of a compromise. Various degrees of effectiveness have been put on the market by various retailers. Some of them cutting corners at the expense of performance, but won't go into that. But you know, it does work, and it will give you multiband operation. Another multiband single wire antenna is the OCF, off center fed aerial. Okay. The straightforward one is referred to as a Wyndham. I don't know where the name come from. Does anybody else know? No? But anyway, it's fed, instead of being fed in the middle, you start off with a half wavelength at the lowest frequency you want to use, and instead of feeding it in the middle, as you would with a dipole, you feed it a third of the way long. It's a higher impedance, so you need to match it, and typically, and the matching you need will vary with height above ground, but it does work pretty well. I've been using one for some years. The one I bought from America. And of course, the Americans, everything is bigger and better in America, including transmitter powers. So the one I got was fairly robustly built, unfortunately with the price to match, and it also used good quality ferrite, which meant that it could not only be used on the HF bands, it could also do a halfway worthwhile job on 6 meters, 4 meters, and if you're desperate, even 2 meters. So I mentioned the inverted L. There's the inverted L. Does that differ from what a lot of you were expecting? The red is the wire, and the bit underneath the vertical AMU is an automatic matching unit, and so coax taking it to the shack. A lot of people, especially what a lot of people do, unfortunately, is mount it the other way round. And the temptation is a lot of people have the spare bedroom, which of course is upstairs usually, as the shack, and they turn the aerial round, which means they lose half the vertical section, and they take the wire in through a window frame or whatever, and take it in. But you then have the problem: what do you do for an earth? Now, what the unwary do is to drop a wire down from the bedroom the shack window and drop it down to preferably not a flower pot, but preferably a flower bed nearby, and say, that's my ground. And they put their stamp on it by using yellow and green covered wire. The only thing is that the laws of physics don't necessarily agree with the yellow and green wire. What you'll find is that in effect you've got the long earth wire, especially on the high frequency bands, is part of the aerial, so you've got an inverted L, which you are then feeding part way up. Sorry, I haven't drawn the ground. The AMU is sitting on the ground, and so the ground is where the AMU is. I've not drawn in lots of spikes around the AMU. If you want to stick to single band, there are all sorts of options open. In fact, in my early days, in my present location, I had an inverted L, and I was only interested in 3 bands, top band 80 meters and 40 metres for the AFS contest, and so I had a fixed pre-selected ATU for each of those 3 bands, and remote selected it via 12-volt relays. On top band, I switched in a loading coil to bring it up to resonant lengths. On 80 metres, I connected it straight through. It was the right length to be resonant on 80 metres. On 40 metres, I switched in a parallel tuned circuit using some rather nice vacuum relays. Right, so if your aerial is less than a quarter wavelength, you can make up the length by winding wire around into a coil form and putting that in, using that as part of it. You can put one at the bottom, and that may be convenient. As I say, it was with the 3-band system I had. Convenient on top band, but it's probably best to put it about halfway up the aerial if you can. Another dodge you can use is what's known as a capacity hat. You get a nice vertical, which is of reasonable proportions, and where you stopped it, instead of stopping it, you put lots of radials, as it were, on the top, which provide capacitance to ground, which has the effect of lowering the resonant frequency of the aerial. For different reasons, has a similar effect to a loading coil. So that's another. You'll see that done professionally. For instance, in MF community radio stations, that's commonly done. Installation. There are a lot of certain pitfalls you can make. I've drawn, perhaps rather foolishly, my vertical next to a tree. Oh, excuse me. And trees, of course, have sap, which is conductive. So what I've shown is perhaps less than ideal. Should have been. I ran out of paper. Bad forward planning. I should have moved the aerial a bit closer to the vertical, a bit closer to the house. So, and if you haven't got a convenient tree you can hang it from, and you're going to put a mast up, try and make it glass fibre, non-conductive, rather than metal for HF. As already said, with an inverted L, it's good to feed it at the far end, because the problem with bringing it close to the house is that on receive you're bringing it close to a potential interference, as I mentioned, from all the wonderful devices that are commonplace in houses nowadays. Everything just about has it, including washing machines and so on, have microprocessors in them. And BT are now going to change all our phones to, so I'm told, to devices which are digital, which again, potential problem. Also, keep aerials away from TV aerials, from an interference the other way point of view. You don't want to put lots of volts down your neighbour's TV installation. I'm talking about Freeview, of course. And beware of other wiring, telephone cabling, burglar alarms, PIR lighting. A neighbour of mine had huge problems with with me, especially on 6 meters. Every time I switched on, every time I turned the beam in his direction and powered up on 6 meters, it flashed his outside lights on and off. The other thing is that the dipole aerial is fundamentally balanced. If you look at it at the feed point, you're feeding both sides of it with equal and opposite, in 180 degrees out of phase, voltage and current. That needs to be preserved. If you don't, then you upset the balance of the aerial, and you'll find that it doesn't. It no longer works as well as you hoped it would, and it also potentially gives you EMC problems. So if you have a balanced aerial, do use a balun on it. Don't just be tempted to take the shortcut and connect 50 ohm coax straight to it. Oh, I missed out one multiband aerial, by the way, and that's the doublet, which this club has used in past years for HF Field Day. It works very well. It has two disadvantages. One, it has a balanced feeder. That's all very fine in the open air, where you can just drop them down and into an open flap in a tent or whatever. So that isn't too much of a problem. You do, though, need, of course, an aerial matching unit, and you need one that will handle balanced feeders. Not all will. So that's the doublet. Apologies for leaving that out. It wasn't intentional. It works very well as an aerial, and is quite popular with HFers, if I may put it that way. Let's talk about transmitters and power. All right. Now, if you've got 10 watts from a transmitter, say, then you want to radiate it all round, you will need something which doesn't exist, which is an isotropic radiator. And that will radiate equally in all directions. So it's a polar diagram of a balloon, if you like. Yeah? Next step along from that is the dipole. Yeah? And the dipole is directional. It has minimum radiation off of the two ends, and it has maximum front and back, or for a horizontal dipole. And a dipole has a gain of around, is it 2.2? I can never remember. 2. All right, I stand corrected. For a gentleman in the back, 2.15 dB over an isotropic radiator, because you are concentrating the power in some directions to a limited extent, at the expense of what happens off the end. All right. Now you can of course take that further. An aerial which is multiple wavelengths long, you can extend an aerial. What you will find is you finish up with multiple lobes and some dropouts as well, some nulls, especially on the higher frequency bands, and you are of course then concentrating power along the lobes, and that will indeed give you gain over a dipole, but it's at the expense of loss of signal in other directions. So, think of a car headlight, if you like. 60-watt bulb, a naked 60-watt bulb. What does that do in the open air? Not a lot. But you concentrate it in a beam, and but at the expense of losing power, lighting power in other directions. I have used for some years now a Wyndham aerial, and this is what it does on the various bands. It's off-centre fed. It's fed a third of the way along. It has a Ballon, I think it's 5-1 or 6-1. I can't remember what I ordered. 4-1. 4-1 works well, provided you have it up at a good height above ground. And as I say, these are the figures. These are the graphs of SWR against frequency for mine. There's 80 metres. It was about 1.75 at 3.5 megs, coming down to about 1.25 at, what was that, 3.775, and then rising a bit. I mean, most people will find that very acceptable. That's 40 metres. The original 70 to 70.1 is fine. It goes up to what's about 2.3 at 70.2, but again, that's perfectly acceptable with a box standard rig with a 3-1 internal AMU. $20 metres, better than 1.5. And I've scanned 400 kilohertz rather than 350 because I was lazy. I couldn't be bothered to work out what I needed to set it to. And right, the problem with the basic Windham is that it doesn't work on 15 meters, but there is a way around that. If you take the original Windham lengths as L and L upon 2, yes, because it's feeding it a third of the way along, yeah. So the longer length is L, and the half length is L upon 2, yeah. You put a short length of L upon 4. In parallel but spread a little, as with the nested dipoles, on the long length. So you then finish up with two Windhams, the original one, and then a shorter one which shares the half length of the original Windham. That's 28. That's 18 megs, which is usable. Below 3, that's 12 metres, 25 megs. That's 10 metres. It is good on the important, well, as far as I'm concerned, the SSB and CW end of the band. I don't know why 50 megs is so poor. But I have used it on 50 megs, used it in several Christmas cumulatives, because at that time I was time sharing the stub mast between 6 metres, 4 metres and 2 metres. So I put 2 metres on the mast and used the Windham on 6 metres and 4 metres, and I made a worthwhile number of contacts. That's 4 metres. And even, I don't think I've ever used it on 2 metres, I've never needed to, but I've certainly used it on 6 metres or 4 metres with, bearing in mind that it's a pretty basic aerial. So there we go. And do take care with the routing of feeders on balanced antennas, such as dipoles. If you're, for instance, run a basic single band dipole, if it runs down the garden from the house to a tree or a pole, then you want to take the coax off it via a balun and bring it into the house. How do you do it? What route do you take? Yeah. Or if it's not straight off, take it at an angle, at right angles to the direction of the wires, take it across to a fence post or whatever, and then drop it down and along the bottom Arris rail if it's if it's your fence. If you do anything else, then the braid on the coax is nearer to one half of the aerial than it is to the other, so the radiation from the two halves of the aerial will not cancel on the outer of the braid. The worst thing you can do is run it parallel to one end of it and just bring it into the shack, sort of suspended below one half of it.